Recording in progress. Welcome back, everybody, to another amazing episode of Meti with a Fantastic Researcher. So today, our fantastic researcher is Leo, who's joining us from IT and is going to teach us all about building performant and brain-like recurrent models from neurons and astrocytes. Leo, we're very excited to have you with us. Really looking forward to learn from this talk. The floor is yours. Please go ahead.
Okay, thank you so much. Thanks for the invitation to talk, and I really look forward to, our conversation afterwards. So, yeah, I'm going to tell you about building performant and brain-like recurrent models from these things called neurons, which you all have probably heard of, and these other things called astrocytes, which perhaps you haven't heard of, but by the end of the talk, you'll know all about. Ooh, there we go. Okay. So just to give some broader framing for who I am and what the type of research I do is, so I'm a computational neuroscientist, which means that I study how the brain works from the perspective of things like computer science, physics, mathematics, and of course, machine learning and AI. And we've seen a kind of interesting trend in the last 10 years, but really going back way longer before that, about computational neuroscience and machine learning helping each other out. What do I mean by that? I mean that machine learning folks have used the brain as a rich source of inspiration for new ideas. And now we're actually in the reverse situation where neuroscience folks like me are using concepts from machine learning and AI also for inspiration. So I'll tell you about some projects I've done in the last few years that kind of go between these two fields. So the first thing I'll tell you about is my recent work relating some AI architectures, in particular modern Hopfield networks and transformers, to interactions between neurons and non-neural cells in the brain, and I'll explain all about what that is. And then in the second half of the talk, I'll tell you about some work I've done taking neuroscience concepts, in particular something called dynamic attractors, and formalizing them mathematically so that they can be put into machine learning systems. And after we did this, we managed to actually build some state-of-the-art recurrent, what are called network of networks, and I'll explain all about that as well. Oh,
Yeah.
is there a question?
Ah merde. Il est long mon mot de passe, hein?
Oh, okay. Maybe it's not for me. I just hear some chatting, but no
Yeah,
problem.
there is a bit of noise. Yeah, no problem. Yeah. Sorry, I think he's just muted. Sorry about that. Yeah.
Oh no, it's okay. I just wanted to make sure I wasn't missing somebody's question. It's not a problem at all. Okay, so just to complete the loop, to give you some sense of idea for what's in store. So I kind of approach these two fields from the perspective of an applied mathematician. So that is, again, using the tools of math, in particular dynamical systems theory, to kind of bridge these two, what I think are interesting fields. Okay, so let's get into it. So, even though we've all heard of neurons, it turns out that not all brain cells are neurons. In fact, you have two major types of cells in your brain. One type of cell is, of course, the famous neuron, but the other type of cell is called the glial cell. And neurons and glial cells are roughly half and half in the brain. The reason they're called glial cells is because the person who first characterized them, this gentleman over here, noticed that they were so abundant in the brain that he thought they were a kind of glue that holds the brain together. And so he named these cells after the Greek word for glue, which is glia. Okay. So just to give you some sense of scale here, you have roughly 86 billion neurons in your brain. 16 billion of those are in the cortex, the most recently evolved part of your brain. And you have roughly 85 billion glial cells, again, averaged across the whole brain. But if you look at the cortex, you actually have 60 billion glial cells in your cortex. So many more glial cells than neurons. If you look at different parts of the brain, for example, the cerebellum, the ratio is different, but averaged across the whole brain, you have roughly half and half neurons and glial cells. So neurons are quite old evolutionarily. They're roughly 500 million years old. And glial cells are also roughly the same age. So the existence of glial cells is coincident with the evolution of the first centralized nervous system. So they're quite ancient evolutionarily. The main differences are that neurons are electrically excitable. So you may have heard of neurons spiking or quickly changing their electrical activity and conveying that change to other neurons. It's kind of the essence of how brains work, or at least neurons work. Glial cells, by contrast, don't spike, and they're quite electrically passive. Instead, it turns out that they compute and communicate with other cells via elevations in intracellular calcium ions, okay? And so to put that in kind of plain English, what that means is that if you want to listen in on what glial cells are doing, you need to do calcium imaging. And calcium imaging is only a few decades old, whereas electrophysiology, which is, the detection of electrical activity near neurons, is like hundreds of years old. Okay, so this is a relatively new field, the study of glial cells, that is. And whereas neurons communicate, quickly over long distances in the body and brain with other neurons, glial cells tend to have more localized impact, and I'll get into what that means. So out of the glial cells, I've been particularly interested, I and collaborators and many other people have been very interested in a special type of glial cell called the astrocyte. The reason it's called an astrocyte is because when you look at it, so here I have an astrocyte cartoon, is that it kind of looks like a star. At least the early staining methods used to look at it kind of looked like a star. So star, astro, cyte means cell. Okay, and these are the most abundant glial cells. Okay, so now I'll tell you about some work trying to understand what astrocytes could be contributing computationally to the brain. And this is a whole kind of series of projects that I've done with my wonderful collaborator at IBM Research here, Dmitry Krotov. So here I'm showing you a picture of an actual astrocyte from the hippocampus or the memory center of a rat. And I've drawn in some synapses nearby to show you the main interesting feature of astrocyte morphology, which is that a single astrocyte can connect to many nearby synapses. And by many, I mean up to 2 million. Okay, so you have this one-to-many connectivity structure. And to kind of turn this a little more into cartoon form so we can analyze it better. So the astrocyte is made out of a main cell body called the soma, this thing in the middle here, and has many of these tentacle-like processes. That's the technical name for them, processes, coming off of this centralized cell body. And if you go down to the end of these processes and zoom in, what you would see is that these processes in-sheath nearby synapses, okay? Forming this three-part structure between presynaptic neuron, postsynaptic neuron, and astrocyte process called the tripartite synapse. And tripartite synapses are so common in the brain that people have just focused on them as a computational unit to be studied. Okay, so what happens with the tripartite synapse? Why do we care? So first of all, it turns out that astrocytes are sensitive to neurotransmitters released in the synaptic cleft. What does that mean?
Sorry to interrupt, but just may I ask a question, please? Yeah, so
yeah, please do. Please.
In this cartoon you have, right? So Bij is the probability that there's a transmission that happens from Xj to Xi, or can you please maybe explain the notation a bit more?
Sorry, yep, that's totally fair. So P here just stands for process, actually. So this is process Ij, and X here stands for the state of neuron I, and Xj stands for the state of neuron J. What do I mean by state? I mean, for example, like the membrane potential. And so this Pij, we think about it as like the level of calcium inside the astrocyte process. Okay. And this S variable here measures how much neurotransmitter is in this synaptic cleft. So how much neurons I and J are communicating to each other.
Got it. Okay. Right. Understood.
Yeah.
So and the value or the level of this Sij depends on the process Bij in some way?
Yes. So you'll see on the next slide, there's going to be way more equations, and I'll explain everything there. But yes, Sij depends on Pij. And for a reason that I'll explain now just with words, and then on the next slide with equations. Does that sound?
Yes, that's absolutely great. Thank you.
Okay. No, thanks. Yeah, and just in general, feel free to ask me any questions whenever. Okay, so astrocytes are sensitive to neurotransmitters. So every time, presynaptic neuron spikes, the astrocyte listens in and elevates its calcium. And again, I'll formalize that on the next slide, but I'm just trying to give you the high-level picture here. There's a bunch of different neurotransmitters that astrocytes are sensitive to. These are just like chemicals. Just to give you a sense of the time scale of response. So on these individual process levels, astrocytes can elevate their calcium just in a few hundred milliseconds, so quite fast. But at other places in the astrocyte, I mean, it seems like they can integrate calcium on a much slower timescale, which is interesting for other reasons. But at the level of these individual processes, it's like hundreds of milliseconds. So I already mentioned a single astrocyte can contact, up to 1 million or 2 million actually synapses. And interestingly, what this enables, or so people think, is that astrocytes can do spatiotemporal integration of neural activity via these calcium elevations that can get distributed across the whole astrocyte cell, okay? And we're going to use this later on when we build computational models and make connections to transformers and all that. And so to close the loop, since these different astrocyte processes can communicate with one another and do this kind of calcium integration, it turns out that astrocytes also release what are called gliotransmitters into the synaptic cleft, which then modulate neural activity. So gliotransmitters are just like the analog of neurotransmitters, but for glial cells. And these are thought to regulate synaptic plasticity, so this S parameter here, and thereby impact learning and behavior, okay? And so these are all things that people have figured out experimentally over the last 10 to 20 years, but modeling and theorizing have lagged far behind. So to summarize this slide, there's a closed feedback loop between neurons and astrocytes, okay? And so we want to understand what could be the computational role of that feedback loop in the brain. And so we're going to build a mathematical model of that, okay? So just to give you a picture of what this looks like in the brain to, have something in your head. So this video I'm about to show you is taken from the brain of a larval zebrafish, which is a very simple type of animal. The reason biologists like to study this animal is because it's translucent, so you could do this kind of calcium imaging very easily. So this is from Misha Aaron's group at Genelia Farms. And on the right here, I'm going to show you the actual neurons in the brain of this animal while the animal's doing some task. And on the left, I'm going to show you the activity from the astrocytes in the brain of this animal while it does that task. And this video is sped up 3.5 times. So initially, you'll see some flurry of activity in the neurons. They spike, activity goes somewhere, something happens, and then you see nice big responses in the astrocytes as well, okay? And these are all calcium indicators that are lighting up, indicating the presence of calcium in the animal, okay? And so we kind of want to understand what all these different interactions are. Okay. Okay, cool. So now to give you some, just to make sure we're all on the same page mathematically, let me start, introducing some notation. So I think in terms of state space models. So what is a state space model? So imagine we have n units where units can be neurons, can be astrocytes, whatever, and these units have a state. And so that state can be like the firing rate of a neuron or the amount of calcium in an astrocyte. Let's just call them x1 through n, where n is the number of units, okay? So to make it really concrete, let's pretend that, we're recording some firing rates from the brain. So I stick an electrode into the brain, and I make that one axis of some state space that I'm interested in. I stick another electrode, I get a different axis, and then a third one to complete the state space, which in this case is just three-dimensional. So the state of this brain at any point in time can be represented as a vector or just a point in this state space, okay? And as the brain does a task, engages in a task, the neurons or the glial cells change their activations. And the consequence of that changing is that you move around in the state space. And the way we think about modeling that is through a dynamical systems lens. And of course, depending on the initial brain state, you could have very, very different long-term behavior. So something like this, for instance. So each line trajectory here represents the state of the brain through time, seeded from different initial brain states. And of course, for any of the dynamical systems aficionados listening, I'm just simulating a Lorenz attractor here. If you're curious about how I made the simulation, I made it in JavaScript during COVID when I was bored during lockdown, and I'll share the code for that at some point later in the talk. But of course, this is a special type of dynamical system. It's chaotic, so it's very sensitive to initial conditions. You could have dynamical systems that are less sensitive to initial conditions. So here I'm showing you a attractor network where depending on the initial brain state, you get funneled into one of so many attractors. And actually, that's how we first started approaching the question of modeling what the function of astrocytes could be. So,
sorry to
oh,
interrupt.
yeah.
Just one more
No
question.
problem.
How do you decide where to place the probes? Because I suppose, like, if you place the probes in different places, you might get different dynamics, no?
You're absolutely right. So that's one of the hardest things about doing any kind of neuroscience. So basically, what people have found over the years is that certain pieces of the brain are thought to be devoted to certain functions. So, for example, the back of our heads, like the occipital lobe, is thought to be devoted to vision. There's parts of your brain, like auditory cortex, that are devoted to processing sound. The front of the brain, like the frontal lobe, is thought to be the seat of higher cognition in people. And so when we decide where to stick electrodes, basically we go based off of what we think that brain area is doing. So if we're designing a task that's meant to study, how animals process sound, then we stick probes into the sound, what we think is the sound part of the brain.
Right. Well, aren't astrocytes all over the brain?
Astrocytes are all over the brain, but just like neurons, it's likely that astrocytes in different parts of the brain have different functions.
Okay. Okay. Cool.
Yeah.
Got you. Thank you.
Yeah, thank you. No, it's a great question. Important. Okay. So the way we started thinking about what astrocytes might be doing was from the perspective of what are called Hopfield networks. So if you've never seen Hopfield networks before, I'm just going to briefly explain it. So Hopfield networks are a state space model, essentially. They're recurrent neural networks. And they were introduced by John Hopfield in 1982 in a quite famous paper that sort of launched a generation of physicists into computational neuroscience. And so I'll tell you about that, and then I'll tell you about a recent important generalization of Hopfield networks from Dimitri and Hopfield himself. So the way Hopfield networks work is that they're, again, recurrent neural networks that are thought to have some sort of energy function. If you're coming from control theory or something like that, this is just a Lyapunov function. And so the idea is that as the recurrent neural network evolves in time, there's some sort of energy, a scalar quantity, which is getting decreased along trajectories of your system, okay? And depending on where you start, you're going to end up at different places in the energy function. And Hopfield back in 1982 realized that you could use this mechanism to store memories. So Hopfield figured out a way how to put particular memories, so things that you want to store and then later recall, as the minima of these bosons in the energy landscape, okay? And so when you initialize the state of a Hopfield network or the state of a brain, you initialize it close to one of these bosons, and then you fall into the bottom, and that's the mechanism of memory retrieval, okay? And if I were to start at a different point, I would fall into a different boson. And so you could store many different memories in this way. So recently in this 2016 NeurIPS paper, Dima and Hopfield figured out how to store many, many more memories. So up to K memories, using essentially the same mechanism of a decreasing energy function. But what's the catch? The catch is that when you look at the connectivity that's required in a classical Hopfield network, you have these kind of bipartite connections where two neurons will connect at the same synapse, which is very reasonable to think about because that's actually how neurons link up in the brain. But when you look at modern Hopfield networks, what you need are these higher order connections where many neurons connect to the same synapse, okay? And this is not something that we see in the brain. But nevertheless, you can analyze the memory capacity of these networks just theoretically. So you can ask, how many memories can I reliably store and retrieve? And the answer is, for classical Hopfield networks, the maximum number of memories that you could store scales linearly with the size of the network. So here n is the number of neurons. So if I want to store 100 memories, I need on the order of 100 neurons, okay? But for modern Hopfield networks, you can get polynomial scaling or even exponential scaling, actually, depending on how many neurons connect to a particular synapse. So in general, the rule is, if you have n neurons connecting to the same synapse, your memory capacity is going to be going to have a reduction of 1 power here. So here you have 3 neurons connecting to the same synapse, so your memory scaling is like n squared, okay? So modern Hopfield networks are a theory of doing really
Hello, guys. Can you still hear me? Is it me or is it Leo on his side?
Okay, I'm just
Leo, sorry. I think my connection went down for a while. Right.
Oh no,
Right. Can you go back one slide, I think?
Sure. Here?
Yeah. Okay. Yeah. We can go from here, I guess. Yeah. No problem. Sorry about that. My connection somehow went down.
No, it's okay. So do you want me to re-say this slide, or do you want me to just like go into the next slide?
I think we can go to the next slide. I think we ended here where you were saying about the connections and so on. So I think we can go next. Yeah.
Got it. Okay, no problem. Okay, I just have to hide the like speaker panel on Zoom because then I can't read my slides. Okay, there we go. Okay, so all right, so we asked this question, is there a way to think about this whole tripartite astrocyte synapse story as kind of implementing a modern Hopfield type network? And the answer is yes, and we can do it quite naturally. So let me show you how that works. So first we start with the classical Hopfield network. So what are the equations for that? So here, X, again, you can think about like the membrane potential of a particular neuron. Tau is some time constant, minus lambda X is some like leak. So in the absence of inputs from other neurons, this neuron's activity is just going to decay exponentially to 0. And then, of course, neurons like to talk to each other, so they get input. This neuron I gets input from all the other neurons. And these Gij terms are just the synaptic weights connecting neuron I to all the other neurons. And phi here is some sort of monotonic nonlinear function which converts membrane potentials into firing rates, okay? So this is a classical Hopfield network, nothing new. So then we looked at models of Hopfield networks that have synaptic plasticity because, again, it's thought that astrocytes have something to do with regulating synaptic plasticity. And so Hopfield and collaborators have this paper from 1992 where it's the exact same model, classical Hopfield network, except now these synaptic weight terms have plasticity, so they're evolving according to their own rule. From a machine learning perspective, I mean, I know Jeffrey Hinton has done work on this and calls them fast weights. So this is very much related to that. I don't know who did it first. But essentially the point here is that you have some plasticity that's updating the synaptic weights between neurons in your network. And in this particular case, it's a Hebbian update where you increase the synaptic weight Sij if the neurons I and the neurons J have correlated activity, okay? And so to this, what we did is we said, okay, well, we know that astrocytes can modulate plasticity, so let's just add an additive term, which is meant to model the contribution of the astrocytes. So you could think about it like the amount of gliotransmission. And this psi term here is just some, again, monotonically increasing nonlinear function of P, which, if you recall, is the amount of calcium in the astrocyte process, okay? So this is just some mapping between the amount of calcium and the amount of gliotransmitter that the astrocyte spits out into the synaptic cleft. And if you remember from a few slides ago when I was talking about astrocyte biology, these different astrocyte processes talk to one another. And this scary looking equation is how they do it. But if you just let me break this thing down, it's actually not so bad. So here, Pij, again, is the amount of calcium in the ijth process. In the absence of input from other processes, it'll just decay exponentially, right? Gamma here is some positive leak factor. And this summation term here is just saying that, process Ij is getting input from all the other processes KL, and the inputs that it's getting are weighted by these coefficients, which are stored in this 4D array, Tij-KL, okay? And the reason why there's 4 indices is because the astrocyte processes are indexed by 2 letters, right? So this is just how astrocyte process KL talks to astrocyte process IJ, okay? And then you have a term here, GIJ, which again is just the state of the synapse itself. And this is just saying that the astrocyte process IJ senses the activity, the local activity of the synapse IJ. So this is just how we formalized, as simply as we could, formalize this feedback loop between neurons and astrocytes, okay? So this is just a mathematical model. We think that it's well-founded. We talked to biologists and, they agreed. Hopefully they didn't just agree. There was a reason why. But what can we say about this model? Well, we can say that it has an energy function, just like the traditional Hopfield network and modern Hopfield network. And moreover, we can show that the equilibrium points computed by this neuron-astrocyte network are the same equilibrium points as computed by modern Hopfield networks and are just given by satisfying this equation. And again, for the dynamical systems aficionados, the way we actually prove this convergence is using Lassalle's invariance principle, which is the first time I ever used it since actually learning about it in grad school, which was kind of fun. But the nice thing about this correspondence is that, we can play this game of asking how many memories can we reliably store and retrieve in this biological network, this neuron-astrocyte network, okay? So the way we do that is, so
Leo, can you, yeah, one question, sorry. So this tensor you have, TIJKL, does that depend on the connectivity graph or something, or what is it actually?
Oh, so this actually defines the connectivity graph.
Right.
So this is saying, sorry if that wasn't clear. Let me go back. So, this drawn in circle here is like process IJ, right?
Yeah.
And then now imagine this process over here is process KL. So somehow these two processes communicate to each other through distributing calcium via the astrocyte.
Mm.
So we just phenomenologically capture the strength of that interaction via this term here, TIJKL, which is just a number, right? And we just store these numbers in this tensor here.
Right. But if I wanna go computational on this, right? To store more memory, do I need more connectivity?
Yes, in fact, that's a wonderful question. If you let me, I promise.
Okay, sorry. Yeah.
No, you're actually assisting me here. You're helping me out. It's a great question. And I address it at the very end of this slide, but it's in fact the exact correct question to ask for a reason that I'll say just in a moment. Okay, so, and if I don't answer your question satisfactorily, please tell me and I'll try again. But I think I can do it by the end of this slide. Okay, so the idea here is that you have a collection of K vectors that you want to store. We think about them just as binary random vectors, but they could also have some structure. It's easier to prove things when they're random and binary. And the way we store them is through this very specific learning rule, essentially. And so this is going back to the previous question about what is TIJKL? So it's the weight between two different astrocyte processes. And so if you want to store some arbitrary collection of memories, here's one way you can do it. So you can basically have this TIJKL be like the outer product of these vectors that you want to store. This summation mu here is running over the memory index. Okay. And these I indices are just the indices of the astrocyte process. Okay, so you could think about this like a kind of Hebbian-like learning rule, like a correlation-based learning rule. And so one thing you could do is analyze the memory capacity per compute unit of this network, because, and this is my attempt to answer the previous question, you could reasonably look at this work and say like, okay, yeah, I mean, your memory capacity could go way up, but you've also added a bunch of new units. So how does the scaling actually compare to the scaling of like traditional Hopfield networks, okay? And so we can just look, right? I mean, so we have n neurons, we have n squared synapses, and then we have one process per synapse, so that's n squared processes. So for large n, that's just going to scale like n squared, right? And that's the number of compute units. It's roughly n squared. the memory capacity of this network, you'll just have to take it on faith, goes like n cubed. We can just calculate it, okay? And so if we look at the memory capacity per compute unit, you get n cubed over n squared. You get something that scales with n, okay, which actually turns out to be the highest memory capacity per compute unit of any biological implementation of modern Hopfield networks, and probably of associative memory in general. Okay, so you might notice that maybe the correct thing to look at is not the number of compute units, but instead the number of parameters. And you would be right to pick up on that, because that's actually a fundamental bound just given by information theoretic arguments about how many parameters you need in your model to do associative memory, right? So you can imagine that if you want to store k memories and each memory has n bits, then you roughly need on the order of k times n parameters somewhere in your model, okay? Just arguing heuristically. So if you want k to be n, so you just want to store a number of memories that's linear in the number of units you have, then you need roughly n squared parameters, and those are the n squared parameters of your typical n by n synaptic weight matrix in a Hopfield network. If you want to store n cubed memories like we do here, then you need n to the 4 parameters in your model, and hence the 4-dimensional object here. Okay, so that's really the scaling, and that's true of any associative memory model. The thing that we do is that we saturate that upper bound. I mean, modern Hopfield networks saturate that upper bound. This is a biological implementation of how you might saturate that upper bound in the brain. Okay, does that answer the question?
Yeah, it absolutely does. Yes. But that raises another question for me. Like,
Sure.
when we are implementing things on a computer, we're not necessarily kind of limited by the biology, right? So couldn't I just go as much scaling as I want? Is that one of the reasons why these big models actually tend to memorize things and stuff?
Yeah, it's a great question. So yeah, if you don't care about biology, then you don't care about this work, because the thing that we're interested in is making a biological argument. But you're totally right. I mean, you can go, like, if you're just interested in storing and retrieving memories, you should just use modern Hopfield networks, because they just give you a recipe that can be implemented in computers and there's no issue.
I see. But that
Yeah.
would not be biologically grounded, so to say, right?
Exactly. Yeah. I mean, for
Okay.
better or worse, we're some kind of computational biologists, so we're trying to understand how the brain actually does it.
Yeah, makes sense. Yeah,
Um,
got it. Yeah, okay, understood.
yeah. But the argument I gave though just now about like the fundamental upper bound for how many parameters you need for a given desired number of memories stored, that's actually true for any implementation. That's not limited. That's not a biological argument. That's true broadly.
Yeah, this is very, very exciting, right? Because maybe this result would connect, right, to what we see today in these big models.
Could be. Could
Yeah.
be. Yeah. So actually I'll use that as a segue a little bit. So one feedback we've gotten on this work is that we require a large amount of structure in this TIJKL tensor to get anything to work. And so one reasonable question is, okay, what happens if TIJKL isn't super detailed and well-defined in this way? Like, biology is squishy and noisy. Things might not work exactly like this. And so actually I'm telling this story a little bit in reverse. So this is currently a preprint, this work I'm telling you about, soon to be in review, hopefully. But we have another paper from last year on this same topic where we thought about transformers. And actually, it turns out transformers are just a simplified version of the model I just told you about, the modern Hopfield energy-based network. So again, warning, this is going to be a little technical, but then after that, there's fewer equations. So of course, transformers have taken over the world, for example, in large language models. But they were developed by, machine learning people at Google who, as far as I know, weren't thinking at all about the brain. Yet, interestingly, we actually do tend to see some sort of correspondence between internal representations in transformers and internal representations in the brain as, transformers and humans do the same task. Okay, So this has prompted a lot of people in computational neuroscience, myself and Dima included, to wonder about, in what sense can we regard transformers as models of the brain? Is this just ridiculous? How could we actually do this if we wanted to? And, one of the main obstacles is this self-attention thing that's inside of transformers, that, transformers were introduced to replace recurrent neural networks. Recurrent neural networks, maintain a hidden state of everything that they've seen in the past, hopefully, and can kind of do processing like that. But transformers work in a fundamentally different way where they don't maintain a hidden state. Instead, they just compare tokens. For example, here I'm showing you a natural language processing setting. They just compare tokens to one another in like a pairwise setting, okay? And this raises two immediate challenges for interpreting transformers as biological circuits. One is that naively, this requires a temporal memory buffer to store these tokens in time. Because to compute the self-attention matrix, you need to do all these pairwise computations, which simply means you need to store these tokens somewhere, okay? So that's thing number one. Thing number two is that if you look at the nitty-gritty details of how, self-attention is computed through the softmax, one way to think about it in terms of neuroscience is that you kind of need to do synaptic integration across space and time. So in other words, you need to have synapses sharing information with one another, and you need to do it in a way that integrates information across the whole sequence that you're showing the transformer. So the whole sequence of tokens, okay? And so we thought about this, and we realized that actually, again, that this unique morphology of astrocytes of one-to-many connections could actually implement something like a transformer. So to make that a little more concrete, imagine you have some collections of key, query, and values. We don't worry too much about how these key, query, and values are actually computed in the brain. They're just some sort of linear transforms of your token sequence X. And we build our neuron-astrocyte network. So here, these equations mean the same thing that they meant in the previous slide. So X is membrane potential, S is the amount of neurotransmitter released in the synaptic cleft, and then P we think about as the amount of calcium in the process. But you'll notice a few things are different, like I've added some biases, and also TIJKL is missing, okay? And that's because what we want, it turns out, I'll show in a second, what we want from this astrocyte layer is not a detailed communication of calcium here to calcium there, or something like that. Actually, we just want the calcium levels to equilibrate across the astrocyte. Okay, so to put that in a different way, we want the astrocyte processes to synchronize to the same value. And again, what we're trying to do is to somehow biologically compute the self-attention. And so if we pick the activations carefully, and we pick the biases carefully, and we initialize things carefully, then you can show that this system of equations, this just neuron-astrocyte system of equations, has an energy function just like before. It converges to some equilibrium point, and that equilibrium point is the output of self-attention. Actually, that's not exactly technically correct. It's approximately the output of self-attention. And this approximation gets better as the number of neurons increases. So if anybody's listening has studied linear transformers or transformers that use these kind of random projections, that's essentially the same trick we're using here. And we can look at the performance of our neuron-astrocyte network. We could look at the difference between the output of our neuron-astrocyte network to the output of a real transformer. So on the x-axis here, I'm plotting the number of neurons. On the y-axis, I'm plotting the normalized error just between our network and a real transformer. This is a log-log plot. And you can see that the error is steadily falling as the number of neurons increases, okay? And the thing that sets the context window is this parameter here, M, which is coming from kind of astrocyte plasticity. So basically what this is saying is that the astrocytes have to maintain a running sum of some sort of nonlinear projection of the key vectors, okay? Of course, in biology, things can't compute perfect running sums, but it's reasonable to think that maybe astrocytes can do a kind of like leaky integration of this term, in which case you would kind of get a leaky transformer. But in theory land, at least, we just let this running sum be perfect, and we can just prove that this thing converges to an equilibrium, and that equilibrium is approximately the output of self-attention. Okay, and so just to summarize the point of this plot, this is a simplified version of, the modern Hopfield network I showed you before, which had detailed TIJKL, but in this case, TIJKL is just set equal to 1, essentially.
And this initialization, what does it mean?
Yeah, so this initialization is basically, I mean, there's a few things going on, right? So let me, yeah, unfortunately, I probably should have had a more detailed part on this slide, but when I give talks about this, usually neuroscientists don't want to hear about the details. But basically, so this H matrix here is just like, you could think about it as a Hebbian layer between your value vectors and some sort of, again, nonlinear readout of your keys. So these are just outer products, right?
Yeah.
You can learn, like, you could think about the sum of outer products just as Hebbian learning. So again, correlation-based plasticity.
Mm-hmm.
And that's going into your synaptic layer, which is fine. And what the process is doing here is that it's modulating the how quickly neurotransmitters leave the synaptic cleft. Okay, so higher levels of astrocyte calcium means that things get washed out more quickly. So that's just physically what's going on. Your question is about this initialization here, I think. And so I don't have a better answer than this is. I mean, the way we pick this initialization is because we needed things to just in the same way, like in Hopfield networks, where you initialize things close to the basin of attraction and you fall in. It's much the same picture here. So you need to initialize things in such a way that you provably converge to the desired output. But essentially, one way you could think about it is that these M terms here are like the weights between the tokens and the astrocyte. And the way you pick those weights is through this kind of presynaptic learning rule, which is just keeping track of the sum of these keys.
Right. Okay. And
Yeah.
so in short, what you're showing here is that really transformers and maybe linear transformers, so to say,
Yeah,
are
linear. So this is all linear transformers. Yeah.
are like a special case, right? Like they're kind of biologically plausible in a way, no?
That's the argument. Yeah. I mean,
Yeah.
so it wasn't clear, at least it wasn't clear to me before this work, if linear transformers were biologically plausible,
Yeah,
or
exactly.
transformers at all. So that was the motivation. So the claim here is in fact that transformers, at least linear transformers, are biologically plausible if you believe that astrocytes can actually do these things, which we've tried to argue through, referencing experiments and things like that, that in fact it's quite reasonable to imagine that astrocytes are doing these things.
Got it. And to extend to nonlinear transformers, the math breaks down? Like you couldn't prove things anymore when you go nonlinear transformers?
No, yeah, because precisely for the reason, I mean, yeah, as you say, the math broke down. I mean, maybe someone smarter could figure it out. But essentially what I needed, or what we needed in this work, is to somehow keep a track of this running sum, because otherwise, it would be very hard to imagine how a biological circuit could keep track of the exponential dot product.
Yeah, I see.
Keys and queries across time, right? So it's precisely this like linearization trick in linear transformers that allows you to implement it biologically, because you don't have to keep track of like, the sum of exponential dot products. You just have to keep track of a running sum of keys, essentially.
Yeah. And I mean, in fact, that could explain the improved memory compared to like, standard transformers, right?
True. Yeah. And definitely also efficiency.
Yeah. Okay,
So,
got it. Thank you.
Yeah, of course. So,
Sorry, could you please elaborate a bit more about what you call linear transform? Does it mean that the activation is linear?
No, sorry. So yeah, it's a wonderful question. Apologies for not explaining it. So the idea basically, so what I'm showing here in this sum is like the pure pure output of self-attention. So this is really what's going on. I mean, this is just the softmax self-attention, right? And so the idea of linear transformers, which is not our idea, of course, but is that you want to be able to separate out this exponential dot product here into just a dot product between two feature maps, phi. So I somehow want to write down, this exponential dot product as like some phi of k transpose phi of q. Okay. But it turns out that, with the exponential, you can do that. The catch is that the feature map needs to be infinite dimensional. So this goes back to like the kernel trick and all that. And so what we argued, and I mean, this is like the idea behind these, random linear transformers, like random Fourier transformers, is that it's possible to pick phi as some kind of like nonlinear random projection such that the dot product of this phi of k with this phi of q is very, very close in a probabilistic sense to this like pure exponential dot product. Does that answer the question?
Yeah. Thank you.
Yeah. Okay, so actually I realize okay, so I have a few more slides and then I realize I'm running a little slower on time, so I'll probably just open it up to questions. I actually have a whole other half of this talk, but I'll just leave it after this section. Okay, so what this enables us to do from a biology perspective, like why this was exciting to us, is because this correspondence between quote unquote pure transformers and these neuron-astrocyte networks means that we can take off-the-shelf transformers that are trained on some interesting task domain, like natural language processing, or in the future, some neuroscience tasks that we care about. And we can splice out the weights and just put them into our neuron-astrocyte network and get quantitative predictions for the activity, for what we think the activity of the astrocytes should be as these networks do some sort of task, okay? So there's no actual new information in this plot I'm showing you. This is conveying the same thing as the previous plot with the decreasing error as a function of neurons. So this is just on the y-axis showing the true softmax normalization plotted alongside the astrocyte calcium activity. X is a function of time, which is just the position of the token in some sequence. So in green here, you have for a small number of neurons, the astrocyte calcium. And you could see it's quite far away from this blue curve here, which is the true softmax normalization. But as I increase the number of neurons to get this gold curve, you could see that the gold curve corresponds much more closely with the true softmax normalization. So again, just conveying the same thing I showed you before, but giving you some context for why, as computational biologists, we would care about this thing at all. And of course, you could do the same thing for vision. It's basically the same story, okay? So the takeaway here, the high level idea, if you don't remember anything about what I've said, just remember this, is that astrocytes can adaptively control synaptic plasticity. That's something that's been shown experimentally by actual biologists. And here we try to formalize what that could mean from a computational perspective. Can we actually learn anything? Can we build performance systems? And so we took these basic facts about anatomy and physiology, and they kind of led to two new testable hypotheses about neuron-astrocyte computations. So one is this kind of detailed regime, which gave us the modern Hopfield network, which is a high-capacity associative memory network. And in this other less detailed regime, we were actually able to do the kind of core computational operation inside of a transformer, namely the self-attention. Okay. And this is all to say that modern machine learning AI can actually start to offer us some theoretical insights into brain biology, which I think is really cool because typically the story goes the other way, is that people in AI and machine learning get some inspiration from the brain and then use that. But AI and ML have become like sufficiently independent and advanced that us here back in semi-biology land can actually start to learn something in the other direction. I find that really exciting. Okay, so actually, yeah, I'm going to skip the second half here and then just skip and thank everyone I worked with. So apologies about that, but this would probably be too long. So let me just thank all my collaborators and funding sources and thank all of you for listening. And I'm very happy to stick around and answer questions and all that. So thank you.
Thank you so much. This was amazing. I mean, super awesome, super awesome.
Oh,
Really
thank you.
cool, really cool stuff. So sorry for the internet problem, but this was fantastic, actually. Thank you. Yeah, I mean, there's some people listening. I don't know if they have any questions. If not, I also have some questions I would like to ask, but maybe just give them a chance to do that. Any questions
Sure.
from the audience?
I could ask a couple of things, if that's okay.
Yeah, of course.
Okay with me? Yeah.
Hey, so yeah, thanks also for this fantastic talk. I learned a lot of things, and you actually answered many of my questions even before I asked, so that's great. Double thanks. So yeah, I just want to ask, structures like modern Hopfield nets are sometimes hypothesized to encode episodic memory in the hippocampus, right? Even before we start talking about astrocytes. Yeah, which, as you probably know, is more linked to short-term episodic memories, which are then slowly passed to the cortex. Do you think that what you're describing might be the biological mechanism that encodes, longer-term episodic memories in the cortex, like since astrocytes are so ubiquitous everywhere?
Yeah, I love that question. Thank you. That's an awesome question. So let me try to, without like having to go all through my slides, let me go back to the astrocyte stuff here. So let's see, where do I want to go? Yeah, I guess this is good enough. So sorry. So yeah, the thing with, so this question of, where the memories are actually stored. So one way to view this work is that we're arguing that the long-term memories in the brain can actually be stored inside of astrocytes, inside of this TIJKL tensor here. So somehow that's, I mean, we're thinking about now how actually we don't yet have particularly strong arguments, just, some experiments we could point to that don't invalidate this hypothesis at least. But that's where we think the long-term memories are actually being stored. If you look at just the form of these equations, what we're saying is that somehow astrocytes are kind of guiding the short-term plasticity inside these networks, and they're doing it in a way that depends on the long-term memories which are stored inside of this thing. And so I think I hope I'm answering your question. Please correct me if I'm wrong, but we're arguing that the long-term memories are stored inside of the astrocytes and they kind of modulate the short-term plasticity, but of course, it's an emergent system, right? So
No, you absolutely do. You absolutely do. Thanks very much. If I may, I also want to ask, first of all, I saw that one of your collaborators is Professor Miller, so I want to ask something related to basically, do you think that there's any relation with synchronization of cortical oscillations?
So yeah, that's another wonderful question. So yeah, I mean, Earl was actually one of my co-advisors in grad school. Yeah, so I definitely think that there's synchrony there, pun intended. Because I mean, we know that in some brain systems, I'm trying to remember specific papers. Like I know Raphael Yusta has some work on this. Like astrocytes do regulate, up and down states during sleep, which are like big synchronous events in terms of neurons. And I know there's been some computational work looking at the role of astrocytes in modulating things like synchronization. And so I think, yes, and I mean, to go even one step further, like this morphology of astrocytes I keep talking about, where you have like one to many, I mean, it's kind of ideal. I think this is what you're picking up on. It's kind of ideal for like getting something like synchronization, right? Because you have,
exactly.
right. So yeah.
Sorry.
Mhm.
And
No.
final question, I want to ask if you think there's, they might be related to how something analogous to backpropagation might be implemented.
So yeah, we're thinking about that a lot right now. We don't have concrete ideas enough for me to feel comfortable saying one thing another, but I promise if you check back on this line of work in I don't want to jinx anything, but let's say a few months, we'll have something.
Okay, fair enough. Thanks so
But
much.
yeah, that's a great question. Yeah, thank you for the awesome questions.
Amazing, thank you. I have two more questions, and then
Sure.
we'll let you off the hook. One is
Okay,
technical, one is less technical, right? The technical question is a bit more general, right? So today there's a lot of argument in the way we train these machine learning models about next token prediction, and that's the enabler for artificial general intelligence, right? I always wanted to ask a computational biologist this question and actually take your thoughts on this, because to us it seems that there needs to be some planning embedded somewhere. At least like if my brain, if I think how my brain thinks, it's kind of I have sub goals I arrive to in my thinking and so on, and it's not just I'm predicting next word, I would say, or something. So what's your take on that?
Wow. Yeah, so I mean, that's a wonderful question. I think that goes far beyond like just astrocytes, right? I mean, that's a question about like human cognition in general. I mean, I definitely think, so my background is kind of, also a little bit in engineering and control, right? So I tend to think in terms of like model predictive control and stuff like that, right? But yeah, I mean, essentially, I think that like a large part of the whole like edifice we have in our brains, right, is devoted to building models about how the world works. And you could use those models to then plan effectively, right? So for sure, I mean, I'm not an expert in how LLMs work by any means. You would tell me all about that, I'm sure. But my understanding is that they don't have a lot of explicit world modeling built in. And so therefore, it's like quite hard. Yeah. And I mean, for me, that's the sort of obvious thing that humans do is we have a tremendous amount of world model building in our heads, right? I'm trying to like, so, I mean, biologically, people think about that, at least in humans, as happening in the frontal part of our brains, in like frontal cortex, right? So, I mean, the evidence for that is if you've ever heard the name like Phineas Gage. Yeah. So Phineas Gage, just for anyone who's listening and doesn't know, Phineas Gage is a kind of what you learn in a systems neuroscience 101 class. He was a gentleman that was working on railroad back in the 1800s, I think, who unfortunately had an accident and a tamping rod, went through his prefrontal cortex. He miraculously survived, but his personality was completely changed. And one thing that seemed to be really effective in Phineas Gage was his ability to form like concrete goals and plans. And my suspicion is that that has something to do with his, the destruction of the part of the brain that does world modeling. So that's probably a much longer answer than you were looking for, but yeah.
No, it's awesome actually, because I really want to take like different views on this, because do you think it's possible to get a world model without being embodied in the world?
So my take on that is I think it's impossible, actually. I do think you need to be embodied. And that's so, okay. I just cannot resist this assist, actually. I'm sorry. So one of the future aims for this astrocyte work is precisely, oh, sorry, this is not the slide I want. This is the slide I want. Is precisely that. So one of the things we're looking at is actually embodying these neuron-astrocyte networks into visually rich simulation environments. So here I'm showing an example of one of our artificial agents, the environment that it would kind of grow up in. And it has a body. It's a simple larval zebrafish model, essentially. But because, yeah, I mean, I feel quite strongly actually that to build up a world model, you need to interact in some sort of like complex embodied situation. And I could even show you, we have a little demo of our agent that can swim around. And this thing is driven by neuron-astrocyte networks that are optimized via deep RL to do some biologically relevant tasks. And so precisely, yeah, not only do I believe that, I mean, I'm doing a big project on it.
Right. I see. Interesting.
Yeah.
But because I was thinking like do you think this should be active or passive? Like what I mean is that imagine I put a brain and then I just make the brain watch so many videos of things, right? Like not interact with it, just through vision. watch so many videos, right? Do you think we will ever be able to abstract at least a world model of how the videos are working, for example? And you know what I mean? I'm not like actively interacting with any environment. You're just sitting down and watching videos, right? Do you think I reach a place where I could actually predict the next frame based on the previous frames, kind of build a world model of that?
I think yes. I mean, you'll be able to do something. I'm wary of making claims about like impossibility in these spheres because I mean, it's not like theoretical physics or something or math where I can prove it. I mean, I will say though that when you think about the evolution of the first centralized nervous systems, I mean, like here on planet Earth, basically brains evolved just to do movement, essentially. To do movement and interaction. Like the whole reason that we have brains is precisely so animals can move around, interact with their environment, and use feedback from their environment in an advantageous way, essentially. So from that perspective, just from the one, n=1 case that we have about how brains evolved on this planet, like it seems that, active exploration
is
and
needed.
brain are just one and the same thing. So yeah, you could probably learn something just by passively watching stuff, but going off of what already happened on this planet, I would argue that to really get like a very good world model, you would need some sort of like active exploration and engagement.
Yeah. We also see that in children, right? Like you see babies, all they do is just move around, and try different things, right? So yeah, it does make sense, I think. Oh, cool. Amazing, man. This was like fantastic. We have one last question, and that's a question we ask everyone, right, who join us, all researchers, because we are also attempting to think about ways to improve our review process. So it's not related to technical stuff, but we are all suffering from a bad review process, quote unquote bad. Everybody complains, at least that's what I heard. So, how was your experience, right? And any ideas that you think could actually improve, especially that you're publishing, maybe not in core ML conferences, more like PNAS, as I saw, and so on.
Mm-hmm. Wow. I have so many thoughts. Let me try to distill them. I mean, so I can tell you what it feels like being on the biology side of things, which maybe I imagine is like different from, ML side of things.
Yeah.
So on the biology side of things, it's extremely slow.
Mm.
Get a paper into a journal, and there's not a lot of shared language between biologists, especially in neuroscience. So like whenever we write these computational papers, I mean, it's likely that at least one reviewer is going to not know any math, which is fine. They could just be a biologist. There's nothing wrong with that. And there's no shared notion of progress. So the thing that I've always really been envious of in the ML world is that you all have benchmarks that are basically agreed upon, or someone proposes like a nice benchmark. And that, from my outsider perspective, has seemed to enable like a lot of really rapid, concrete progress. So that's good. I think that more of that philosophy, at least in the biology world, would be really helpful somehow if we all had some sort of shared benchmarking. People have tried this. There are benchmarking platforms that exist in neuroscience, but then everybody disagrees on what the benchmark should be. Yeah, I mean, that's my perspective. I wish I had something better to say about here's how I think.
To your point, I mean, I remember the time where like computer vision, was launching, and also deep reinforcement learning was starting. I mean, you're totally right. What propelled the field forward was things like OpenAI Gym, right? Like a rigorous set of benchmarks where we all agreed on, and we just tried to get these algorithms to improve, and that led to tougher benchmarks and better algorithms and so on. I mean, I think definitely if we can do that in biology, it'll be amazing. It might be a bit tougher though, because you need real data. Sometimes humans are involved, and so on, right? So it's much harder, I suppose.
Yeah. And I think, I mean, yeah, so it's much harder. I think probably in biology, we'd benefit also from like double blind submissions.
Mm.
Like I think unfortunately, I think there's quite a big bias that comes from, you know, the institution you submit a paper from, or like the advisor or something like that. And, you know, I mean, on one sense, that can be a useful signal if it's like a very trusted scientist. It's like, okay, I mean, you put a prior on, you know, the work they've done in the past, and you ask, okay, well, or you say it's probably going to be good work going into the future, right? But in some sense, I like the double blind format because it tries to take that away at least a little bit.
Yeah, let me let you in on a secret, right? So we claim we're double blinded in the machine learning community, but you know, we have archive and we typically submit and put the paper on archive, you know. So this double blinded thing is just a fallacy we're doing because any reviewer will just Google the paper and know who the authors are, you know. If it was executed correctly, I would definitely agree. But I think today what we have is more like we try to convince ourselves it's double blind, but it's not really double blind.
I guess why not, if I'm allowed to ask a question in return?
Yeah, of course.
Yeah. I guess what are your thoughts on why not just institute a simple policy of like no preprints allowed before?
Yeah, so I think that's a good point. However, the problem with computer science and machine learning specifically is that things are moving so fast. Like things literally are moving so fast. Like per day, we're getting hundreds of papers, if not thousands, really. I mean, it's very hard to keep track of the literature. So I think people are very afraid to get scooped, you know, with ideas, essentially, because like, you know, like if I need to wait 3 months before I put my idea out, then somebody probably would put it out and then I got messed up and so on, right? So this is one, from my experience, from my opinion, it's one of the driving factors for people putting things on archive and even sometimes putting half-baked work on archive, you know, just to like put the flag, it's us, right? And then you know, it's just like because the field moves hilariously fast, it's like seriously crazy.
Yeah, okay, that makes sense. If you're afraid of being scooped, yeah, that's logical. I guess you can't do anything about that.
That's one way, and another thing which I believe is the case is that people want the papers accepted. So if you have a big author, you just put it out there so that reviewers can get biased. That's the other thing related to this.
That also makes a lot of sense. Yeah.
Awesome. All right, Leo, this was fantastic, man. Thanks a lot. And we really learned a lot from you. I mean, I can't, like, it's one of the best talks we've had, seriously. Thank you so much. And
Thank you.
with that, I would like to end this session and like to thank our viewers. And if you have any questions, write them down in the comments below and I'll contact Leo to help answer them. And please feel free to like, share the video, and also subscribe. So we'll see you next week with another episode of Mette with the Fantastic Researcher. Thank you a lot for attending.